Swayam Prabha. Digital India. Educated India.
So with that background, let's summarize. What did we discuss? We said that we want to do the lookup operation. Lookup operation need to be fast enough because the routers are getting so millions of packets per second, particularly if the router is in the backbone of the network. And in order to do that, we have got bunch of options. One option was to implement that in the software, and that software implementation turned out to be a trie structure. We studied the binary and then binary trie structure, and then couple few optimization that we can do in order to minimize the height of the trie structure. But in spite of that, software implementations, whatever optimization that I do, are still slower in operation. And in the worst case, if the entire trie structure is completely full, then you cannot bring any optimizations, particularly at the binary trie level. So you can do the automation, that is, if all 2 to the power of 32 entries are there in the routing table, then you will have the if you use the binary structure, that will be full. You will have worst case performance of 2 to the power of 32 number of entries, and those, that is the memory space, and also the 32 number of the memory references are required, because you have to traverse from one pointer to another pointer. That's going to be quite complex or tedious in nature, and that probably will not scale. Particularly if you go to the IP version 6, then the IP address length is 128 bits. In the worst case, 2 to the power of 128 is the memory size requirement, and then 128 memory references, pointer references are required in the worst case. So that's going to be quite slow. It's not going to scale up. And now the question that we ask is, what is the other thing that you can do? If software implementations are scalable, not scalable, then we turn into hardware. So now the question that we ask is, what kind of the hardware lookup that I can do to do the faster route lookup. So some of the examples that we see, at least a couple of examples that I am going to discuss in this class. And the goal is to do the lookup operation in order of one time. So one memory access should be good enough to do the forwarding operation. So that is the overall goal. So let's see whether that is possible or not using the hardware. So what kind of the hardware and memory access mechanisms that we can do for doing the lookup operation will take. So first I will discuss a simpler architecture of the hardware based route lookup. This route lookup is called as the direct 24/8 basic route lookup architecture, and this is a research effort at the Stanford University, and it is a very simple operation, lookup operation that is done in the hardware. And what it does is it divides the prefixes into two parts. One is the 24 bit up to length 24, 0 to 23, and from 24 to 32, that is the complete address. It has got two tables. The first table holds the prefixes up to length 24, and the second level table holds the prefixes which are longer than the 24 bits, including the 24 bits. 0 to 23 and 24 onwards, it is in the second table. So why this kind of the structure? So this is a very simple architecture. What they did is, they took some of the practical router forwarding tables and looked at the distribution of the forwarding table. What kind of the prefixes are there in those forwarding tables? So it turned out that the majority of the prefixes that are there are concentrated towards the maximum number of the prefixes are up to length 24 or less than that, and beyond 24 there are only few number of the prefixes. And it makes sense to have concentrate all of these prefixes up to length 24 in one table and the remaining ones into another table without wasting the memory size. That is the motivation for this kind of the architecture. So again is the number of is more than one memory reference. So if I have multiple tables, then multiple memory references are required. So you remember in the multi-bit trie, one table 3 bits, second level 3 bits and so forth, it was going. The more number of the structure I got, more number of the memory references are required. So that is going to be slower the operation. So here in this case, I am going to do one level operation up to 24 bits, 0 to 23, and then 24 rounds in the second bit. Only two tables are there, and I am going to store the entries in such a way that one lookup operation or one memory reference when the first level is sufficient and one memory reference is in the second level is sufficient. And why this is the motivation for having this kind of a structure is they came up with the argument that memory is getting cheaper. When I say the memory, this is an inexpensive DRAM memory that is available, and DRAM is cheap and can be used inefficiently. Why inefficiently? Because we are going to expand if any prefixes which is less than 24 bit length, that I am going to expand and then fill it in the first level table. So in effect what I am trying to say is the table 24, the first level table will have 2 to the power of 24 number of the entries, and any prefix which is less than 24 bits, one lookup in the first level table is sufficient. Any prefix which is longer than that, the second level reference is required. In the worst case, two memory lookup, one is the first level and the second level would be sufficient to find out where to forward the packet or the lookup operation is complete. So what it does is, it does the following: the table, the first level table would look something like this. So the table itself is having these slots, and the first level, every index, all 24 0 bits is the first entry, first 23 0 and the 1 is the next entry, and all 24 bits 1 is the last entry that is there in the table. This is how the 2 to the power of 24 bits table is taken, and the width of this entry, one entry is the 16 bits. So when I reference, let us say the destination IP address is something like this: 10101010104812 and then 101016 1010 20 24 28 32. So what I am going to do is take the first 24 bits, 16, 20, 24, up to bits from starting to this one, and then I go to that memory location, meaning whatever the memory location which is all 101010, that memory location I go. Let us say this is the location that I get for that one, and this value is whatever the entry that I get after referring to this is the 16 bits, and I take that, and depending upon whether this is actually indicating or representing a prefix which is lesser than 24 bits or greater than or equal to 24 bits, I decide whether the second level memory reference is required or not. So how do I determine whether the second level reference is required or not? Is by looking at the entry, it is 16 bits. If let us say the 16 bits are something like this, I get 0 0 0 0 0 0 something like this, 1 1. So if the first bit, in this case the entry that out of the 16 bits is 0, it represents a prefix which is less than or equal to less than 24 bits, and I do not require the second level reference, and then I go to the next, whatever is it is indicating the next level hop, where on which port number I need to forward this packet, I am going to just forward that. If the instead of 0, if the first bit is actually 1, then it requires that this is the prefix, part of that is stored in the which is longer than, prefix is longer than or equal to 24 bits, second level reference is required. I go to the second level and then do the decide. So, depending upon whether the first bit is out of 16 bits, whether this is the first bit is either 0 or 1, I am going to decide whether this is second level reference is required or not. Now, what does the second level table contains? Second level table contains 256 entries for every possible prefix that is there in the first level entry, if the prefix is longer than the or equal to 24 bits. What I am trying to say is, if let us say the entry is 10.10.10/24, and now the first 24 bits are indexed in the first table, and I am going to write a 1, let us say this is the entry 1 followed by something, and these 15 bits, secondary level 15 bits indicate in the second level table where exactly the 256 entries correspond to the remaining possibilities. What is that? 10, 10, 10.10.10. So, this is there, these two are indicating 24 bits, and the remaining 8 bits can be anything from all 0, 0, 0 to all 1, 1, 1, 1, 1. So, for all these possible 256 possibility cases, 8 bits are there, the remaining 8 bits I do not care, and that is the indication. If I have a /24 prefix, then I do not care about the remaining 8 bits. So, for one entry in the table 1, if the prefix is of the length larger than or equal to 24 bits, you will have 256 expanded a number of the entries in the secondary level table, and the index of the starting index of that entry is stored in the first table. So, that is given by these 15 bits. So, I take these 15 bit entry and then multiply it by 256, I get whatever the index number, I go to that index number, and starting from that is the remaining entries that I am going to get. So, let us take a look in an example that should be clear. So, any prefix which are smaller than 24 bits are expanded up to 24 bits. Let us say I have got an entry which is 10.10/16, this is not 24 bits. For 256 possibilities, what are those? 10.10. It can be 0, it can be 1, so on, it can be 256. So, for all these 256 entries, one entry which is of having /16 is expanded to 256 entries, then stored. If you have something 10/8, then 256 possibilities for the second position and 256 possibilities for the third position, that is the 256 cross 256 time the prefix is expanded and then stored in the first level table. So, that is what is done. So, it is always the first level table is always full. So, to all 224 2 to the power of 24 entries are always there in the first level table. So, if any prefix is less than that, you need to bring it into the 24 into formats. So, in this the example that I show. So, similarly, if you have 10/8, then for this possible cases 256 cases for this one and 256 cases for this one, we expand it and then store it in the table as one entry in the table. So, let us take an example how this will look like. With a let us assume these are the 3 prefixes that I got. One prefix is of the /16, 16 bits prefix 10.54, and 10.54 34, this is the /24 bit prefix, and then the third one I have got the 26 bit prefix because this is the CIDR entry. Now, how does the table in the table 1 and the table 2 structure, what are the kind of entries that I got for these many cases in the table? So, 10.54 is this, if I first is I convert this into binary, I have got a table, the first level table entry, and I convert this 10.54 into binary. So, what is that to look like? The first one look like it is 10 0 0 0 and then 1 0 1 0, the 10 is over, and 54 when you convert it to binary you get 00 110 110. And what are the other third bit, because I need to bring it into cases. So for all entries starting with 0002, so 1 1 1 1 1 1. So I am going to have these many 256 entries are going to be there in the first level table, table 24. So I am going to make these many number of the entries for this prefix in the table number 1, and for all of this the first bit is going to be 00, and the remaining bits are indicating the index into the forwarding table entry on which port number they need to be forwarded. Next top information. Similarly, I have got one entry which is 10.54.34. So 10.54 is common, and then out of that 34 is one possibility among these many combinations, all zeros to 1. So 34, if you convert it into binary, you will get 00 1 000 10, and one among these entries that I have created is going to be reserved for this 10.54.34, and that is the case. And then in the secondary level table, I am going to expand that into 256 entries, because this is the prefix of length 24, and a subset of that, which is the series 10.54.34.192 is the /26. If you convert this number 10.54.34.192, so this is the my 10, this is my 54, this is my 34, and then the last 192, when you convert it into binary, you get 1160 zeros. And so what it means is these say 8 bits here, 8 bits here, 8 bits here, and these 2 bits are fixed, and the remaining 6 bits I do not care. So when I examined, I already made entries for these cases. /34 is already there. 256 entries are created in the first level table, and the remaining some portion of the remaining 256 entries in the level number 2 are now reserved for the third version. So that is what how the table look like. So for the 3 prefix series that we have, the table would look like something like this. On the 24 bit table is this one, and the 8 bit table is the second one. And what we have is 3 entries in the 24 bit table. So the first one indicates, if it is a 0 here, it indicates that the prefix entry for this one is an expansion of the /16 or less than that series, and you don't have to consult the second level table for this kind of entry. So here, let's say you get 10.54.0, then it means that you need to forward it looking at this 24 bit table itself. So the first bit, as I said, column indicates the whether the second level table reference is required or not required, and the second column actually indicate the actual the prefix in the sense 10.53.255 is the previous series entry. That is where it ends, because the entries there are 256 entries starting from 0 to 255, and the next series is actually starting. The first entry of this series is 10.54.0. So that is actually indicated here. This is the first entry of the series 10.54, and the second entry of the same series, and so forth, from here to all the way till you get to 10.54.255. So this series is actually covered in this case. And a subset of that, which is 10.54.34, is actually somewhere here, and that is a /24 prefix. And what we do here is the second level table reference is required, and that's why this is actually marked as 1, and 10.54.34, the third column is actually for the cases where the direct forwarding can be done by consulting this table only. The third column actually has the port number information. Here the port A is one port for 10.54/16 series. Port B is for 10.54.34/24 series, and port C is for 10.54.34.192 series. So what this third column for this entry indicates is it is an index to the starting position of the second table. So the entries corresponding to the expansion of this entry into the second table is starting at the index number 120. That is what it means. So the 120 multiplied by 256, because every expansion from the first table to the second table will have 256 entries. So the what it means is 119 entries starting from the address is already there in this table. So those are here. 256 into 190 entries. This is the starting position of the expansion corresponding to 10.54.34. So this index is that number, and starting at this one, so this indicates that you should forward this with the port number B. So all these entries will have port number B marked that. So 150 multiplied by 256, 256, and the next entry 256 plus 1 plus 2 and so forth. So this is supposed to be 2. There is a correction here. This is 120 into 256 plus 2 and 3 and so forth. So up to how long you need to do that? So the third series is actually a subset of this series 10.54.34.192 up to the point it is 191. You forward it to port number B. The moment you see 192 entry, you need to forward it to port number C. So how long? Till all the remaining entries. What it means is 192, if you convert it into binary, so it will be something like this: 11, 000, and 000. Starting with, I don't care what, 192/26. The 24 bits are actually covered in the previous case, and the 2 bits are kept constant, and from this to all 0 to all 1s till you get this. Yeah. So all 1s. So the entries need to be forwarded with the, what it means is, so I don't care what is the value of the remaining 6 bits. So just 192, 193, 194, everything else till 255 need to be forwarded to port number C. So that's how the table is actually constructed. So let's take an example of particular IP address and how exactly the lookup operation, the search operation in this two table structure is actually done. So the first IP address that I get is 10.54.22.147. So we need to look into in which series this is actually falling. So the IP address is always 32 bits, but the comparison, the way you do it is based on whether it is falling under the first series, second series, or the third series. So if you look at this diagram, so 10.54.34 is the place where the second level memory reference is required, but what we have is 10.54.22, that entry is somewhere here. So that the 10.54.22 is somewhere here. So that is actually falling into the first series. So it says that the best match that you can find is 10.54/16 prefix. So you forward it to the port number A. Similarly, the second entry 10.54.34.23 is actually surely this is falling under the second case, and we need to examine further whether it is going into the third range or not. So 23 is somewhere here, 1, 2, 3, 4, and somewhere here is 120 into 256 plus 23, and remaining up to 191. It is falling here, so you need to forward it to port number B using the second prefix series, which is 10.54.34. And the third one, 10.54 to 34.94, 194, that is actually falling here. The next entry to this one is 120 into 256 plus 194. You need to forward it to port number C. So that's how this table lookup is done. So let me summarize what we discussed for this two-level memory-based hardware lookup operation. The first memory is holding the entries for the 2 to the power of 24 number of the cases. So if any prefix is falling short of the 24 bits, then you do an expansion and create entries for all of them. And whatever the expansion that you do for all of them, you need to write the port number of the same series with which you have done the expansion. And in the if the prefix is more than 24 bits, then the second level table reference is required, or the memory reference is required, and that is indicated by the writing 1 in the first column. And then you, for every entry in the first table memory reference, you have got 256 entries in the second level table. So if the entries are representing less than 24 bits, then the port number information is kept in the third column. Otherwise, that will store an index to the starting point for the expansion of this series, which is indicated in that particular IP prefix. So that's how with two memory references. First one, you find out in the 2 to the power of 24 table, 24-bit table, and then the next one is the 8-bit table. So that's how this lookup is done. So although this lookup is able to do the quick search operation by having two-level memory structure, so the sheer number of the entries, 2 to the power of 24 entries in the first table itself is quite large in number. So 2 to the power of 24 entries is quite large in number. So by virtue of that, sometimes this table itself will become bulky. And also, if you go to the IP version 6, then surely this 24-bit table will not work. It works only for the IP version 4 address. So that's why this is not used in practice. But nevertheless, this is the first attempt which was made to construct the route lookup operation inside the hardware. So if this is not the best way to do the lookup, then what else I can do? So if you can recollect our previous discussion on the ternary content addressable memory, we said that TCAM can actually do the comparisons by taking in prefixes into account. Basically, some of the bits you can omit and then do the comparison. So TCAM is actually having entries. It is a table and it has got entries for some prefixation. So I can say that 1010 star is the first entry, 1101 star is the second entry, and so forth. So what it means is, given your IP addresses still can be 32 bits, for the sake of convenience I'll write 6 bits here. If you can give an IP address of 6 bits, ignoring the remaining 6 bits, you can still do the comparison. Here in this case, 111011 is not matching to any one of them. Maybe 111011 and something like this is there. Then it can find out, okay, so this is the best match that I can find for you for this particular IP address. So one of the key feature of this TCAM is, although it is doing the content search in the memory location, but the beauty of this TCAM is it can do the search operation in order of one time or in constant time. So what it means is, the hardware, the TCAM memory has been designed to do a parallel comparison. What it means is, so you take the IP address that is given
and the hardware circuitry parallelly initiates the comparison operation by taking contents from each of these memory location. So it will do whether this IP address matches with the what is the entry in the first row, what is the entry in the second row, and what is the entry in the third row, and so forth. So a parallel comparison is done, and immediately after this comparison, so it takes a deterministic amount of time to do one comparison. So taking the entry of this one and with the comparison of this one, it will take deterministic amount of time. And similarly, the second entry will also take a similar amount of time. So in effect, so when with the time of how much it takes, the deterministic amount of time taken for one comparison would be sufficient enough. That is the time taken for the overall search operation, because these operations are done in the parallel comparisons. So that is why TCAM is actually a preferred way of implementing the lookup operation, and moreover it works with the prefix ignoring some of the bits. That works for our perfectly work for our case as well. So here is an example of how a TCAM entry might look like. So I might have one prefix indicating 000, that is the default route entry. So anything that is does not match the rest of the entries are matching with this one. And then somewhere here I might have it's a 25 or 25/24, that is a 24-bit prefix, and something else 25, 25, 28, 25, 191, 164, 24, 25. Here is the next entry, and so forth. I might have a 32-bit prefix, I might have 24-bit prefix, I might have 25, 24, whatever number of the prefixes that I might have, all of them I will be able to store it in the TCAM memory. So when I say /25, what it means? First 25 bits I will consider, and the remaining bits I will ignore out of the 32 bits, assuming this is the IP version 4 address. And then what might happen is, if I get an IP address, more than one entry can find a match. So for example, if I get an IP address 25.25.25.25, so in this case, so this is the entry which is going to match 25.25.25/32. This is the exact 32-bit address. And interestingly, you might also find a match here, 25.25.28/25, and you might find a match here, 25.25.25/24. So the TCAM will come back and say, I found a match here, I found a match here, and I found a match here. Now the question is, which entry I need to take? So there are three prefixes which are matching for this particular IP address. So whether to go with the third one, second one, or the first one. So that resolution of whether I should go with the first match, or whether I should go with the second match or the third match, is resolved by this priority encoder. So every match that is found is actually fed into this priority encoder, and that will resolve the conflict. So whether the first entry, second entry, or the third entry. So here in this case, the third entry is the the priority encoder will come back and then tell that the third entry is the best, longest prefix that is matched here, and you need to go to this particular location and find out what is the port number information that is written there, and you need to forward to this particular packet to that port number. So here in this case, although multiple is a match, the third one gets the preference, and the index, what is indicated by that third IP address entry in this, or prefix entry in this table, would take the preference, and the packet is actually forwarded to that. So that is how actually this TCAM actually works. So I repeat, the first level entry is basically a variable number length prefixes are stored in the TCAM memory, given an IP address. That IP address is fed into this TCAM memory. It does the parallel comparisons, and it might happen that more than one entry will match for the given IP address, and all those entries will be fed into priority encoder, and that encoder will figure out which entry, which is the longest prefix that is matched, and then it will indicate this is the index number of the highest priority entry in the table that actually should with which you need to make the routing decision or forwarding decision. So this is a nice feature. So lookup operation is done in the constant time, and it is of the order of 1. Now the problem is solved. But unfortunately, using TCAP memory will not solve the lookup operation completely. There are certain limitations, practical limitations of the TCAP memory. One is it is of the large size. Because of the parallel comparison that the TCAP memory is doing, the hardware circuitry itself is bulky in nature. So it might have a large number of the flip-flops embedded in it by virtue of its physical size. The hardware chip size actually increases, and if the chip size increases, then you require larger space for the router, and if the router size increases, then the other real estate cost and others will come. It will occupy a larger space, the larger LAC is required, and so forth. So it requires a lot of investment. And one of the objective of the hardware engineers is to minimize the size of the device so that in a compact way you can actually, it doesn't occupy much space, and also there are other advantages as well. So, and the second major disadvantage of the TCAM is it consumes a lot of power. So as the number of the hardware elements inside the chip increases, then the larger amount of the power is consumed, and that will actually dissipate lot the amount of the heat. So on one side it consumes the hardware itself, the chipset itself consumes a lot of power, and in effect if it generates more, it dissipates more heat, then you require a larger cooling equipment, larger capacity cooling equipment to keep this device cool. So then that cooling equipment itself will draw energy or electricity, and larger the capacity of the cooling equipment you have, larger the power consumption you have got, then the runtime cost of the using this TCAM based memory itself will multiply. So first of all, it requires large size, and then it's actually drawing more power, and then in effect, in addition to that, it is actually adding more power consumption in terms of the cooling equipment. That's why, because of these three reasons, the practical chipsets that are available for the TCAM memory is very limited in capacity. So you may not be able to find TCAM chips which can accommodate all the prefixes that are available inside your routing table. So now the question is, your routing table might have entries, but because owing to the limitation of the TCAM memory size, I may not be able to fit all entire entries or all entries in my routing table into TCAM memory. Now what do I do? So that is where the opportunities for TCAM pruning actually come into picture, where we look for opportunities where multiple entries on the routing table can be merged and one single prefix can be created. So here is a table which is actually having 7 prefixes, and for the sake of convenience I have taken the 8-bit prefixes, and the third column is actually showing the net mask. So, and the fourth column is indicating the port number on which this particular packet need to be forwarded. So as usual, I look for, the first thing is to convert these entries. Now they are not in the prefix format into prefix format, taking the net mask into account. So for example, what the net mask for the first prefix says is, you take the first 5 entries and ignore the next 3 bits. So I got a prefix of 10001 star. Similarly, the second entry says that take the first 4 bits and ignore the next 4 bit. I get a prefix of 1101 star. So like that. So net mask is basically you how many ones are there in the net mask, those many bits you take, and the remaining bits, whichever zeros, you ignore that. So that's how you convert the entries in the routing table into prefix format. That is the first exercise, and retain the fourth column as it is. So net mask now disappears from the picture. And now what I do is, for the same next hop information, same port number here, the port number 4 is there and this is port number 4. Any two prefixes which are having the same output port number or the next hop information, you see whether these two can be merged and get one entry. So I can merge two entries only when they are differing by 1 bit. So 1000 is there and 1000 is there, and the fourth bit here, fifth bit is here is 1 and the fifth bit here is 0. I can merge these two entries and then get one entry here. So it does not matter whether the fifth bit is 0 or 1, I still need to forward it to port number 4. That is the meaning of that. So going by the same argument, I can also merge P2 and P3. They are also differing by 1 bit. So I create one entry and both of them are saying that you need to forward it to port number 2. I create one entry here, and P4 and P5 by the same argument can also be merged. So both of them are saying you need to forward it to port number 3. P6 cannot be merged with anyone. I will retain that as it is. So like this, I look for opportunities for merging, and where by merging those entries, I can reduce the number of the entries in my routing table. And if I can reduce the number of the entries in the routing table, I can probably fit it into the limited size TCAM memory that I have got. So that's how the routing tables constructed by the routing algorithms are taken, and then an offline exercise for merging or pruning is done, and you get a reduced table size, and that you load it into the TCAM memory for doing the lookup operation in real time. And remember, this operation, every time you change the routing information, the routing table structure changes, then you need to rerun this pruning algorithm again one more time to get to accommodate the changed prefixes in the routing table. Every time there is some change in the routing table, you need to run this.